Ready to dive in? We're about to unpack these machine learning algorithms, all thanks to this stack of resources you've provided, by the way. We're talking everything from, those eerily accurate Netflix recommendations to self-driving cars.
Yeah, it's a field that's just exploding right now, impacting pretty much every industry out there.
It really is. But before we get ahead of ourselves, let's make sure we're all on the same page. When we say machine learning, we're talking about systems that learn from data. They use that data to make predictions, right? So instead of programming every single rule, we're letting the data do the talking.
Exactly. Think of it like trying to teach a computer to recognize a cat in a picture. So
Hmm.
instead of giving it a checklist, right, like look for whiskers, pointy ears, fluffy tail, we show it thousands of cat pictures. And we essentially let it figure out what are those defining features of a cat on its own.
Okay, so it's all about pattern recognition, but on a massive scale. Now your resources dive into these different types of machine learning. It's not like a one-size-fits-all approach, is it?
Not at all. It's more like choosing the right training strategy, I guess you could say.
Hmm.
It all depends on what you want the machine to actually learn. So you've got your supervised learning, unsupervised learning, and then reinforcement learning. And they each have their own strengths.
Let's break those down. So supervised learning, that sounds like it needs a watchful eye, like a teacher in a classroom.
Spot on, yeah. So in supervised learning, we are feeding the algorithm labeled data, meaning that every input comes with a matching output, so the algorithm can learn by example.
So, okay, if we were teaching our computer to, say, differentiate between apples and oranges, we'd show it tons of pictures labeled apple or orange,
Uh-huh.
and it would learn to classify them based on that training data.
Precisely. And within supervised learning, there are two main tasks. You've got classification and regression. So think of classification as like sorting things into categories. So is this email spam or not? Is this picture a cat, a dog, or your Aunt Carol?
And then regression is more about predicting a specific value, right? Like how much will this house sell for based on its size, location, and that, questionable avocado green bathroom.
You got it. Now, each of these tasks has an arsenal of algorithms, each with its own sort of way of finding patterns in the data. For instance, you've got support vector machines, or SVMs for short, and they're really good at kind of drawing that perfect boundary line between two groups. So imagine like separating cat pictures from dog pictures with a line that's so precise that it never misclassifies a single image. That's what an SVM aims for.
And from the looks of it, SVMs are just one tool in this vast machine learning toolbox. You've also got decision trees in the mix. Those sound a bit more straightforward, like a flowchart for making predictions.
They are. They're very easy to visualize and understand, which makes them great for explaining the why behind a prediction. Then you've got kind of the rock stars of the machine learning world, neural networks. So they're inspired by the structure of the human brain, with these interconnected nodes that process information.
Okay, so while decision trees are like following a clear set of rules, neural networks are more like the complex web of neurons firing in our brains. No wonder they're great at tackling like those really intricate patterns like image recognition.
Exactly. And they are very powerful, but they can be computationally intensive. It's like a supercomputer working overtime. Now, on the other side of the spectrum, we have unsupervised learning.
And if supervised learning is like having a teacher, then unsupervised learning is like giving the computer a puzzle and saying, figure it out.
You could say that, yeah. So in unsupervised learning, we don't provide labeled data. The algorithm has to find the hidden structure and patterns all on its own.
Okay, so no more apple or orange labels. We're just giving the computer like a basket of fruit and letting it figure out how to group them.
Exactly, yeah. Imagine a basket of different colored marbles, for instance. K-means clustering is like an algorithm. It can automatically separate those marbles into groups based on their color, even though we never told it to do so specifically.
That's pretty wild. It's like the algorithm is uncovering these hidden relationships we might not even be aware of. What else can you do with unsupervised learning?
Well, there's dimensionality reduction. Kind of a mouthful, I know. But think of it like this. Imagine you're trying to analyze a recipe with, like, hundreds of ingredients. Dimensionality reduction helps us find the most important ingredients, the ones that truly define that flavor profile.
So instead of getting lost in the sea of data, dimensionality reduction helps us focus on like the most meaningful information. That's pretty handy. Okay, so we've covered supervised and unsupervised learning. What about reinforcement learning? That sounds a bit like training a pet, right? Lots of treats and maybe a few timeouts in the corner.
You're on the right track. So
Where-
reinforcement learning is all about agents learning through trial and error. And they do this within a specific environment. They'll take actions, observe the outcomes, and then adjust their strategies to try to maximize rewards. Just like, training a dog with treats and praise.
So if we were teaching a computer to play a game, it would learn by playing repeatedly and
Yeah.
figuring out which moves lead to victory and which ones result in, a crushing defeat.
Precisely. And this trial and error approach is actually how AlphaGo was trained, which was that AI that conquered the ancient game of Go. It played millions of games against itself, learning from its mistakes, refining its strategies, until it could outmaneuver even the best human players.
Now that's impressive. Reinforcement learning sounds incredibly powerful, especially for like those tasks that involve a lot of decision making, especially in those complex environments. So we've got our three main types of machine learning, but your resources also mention this, like top 10 list of algorithms, almost like a greatest hits collection.
They're a fantastic starting point. We've already kind of touched on a few of them.
Ah.
SEMs, decision trees, k-means clustering. But let's take a quick tour of these heavy hitters. We'll start with a classic, linear regression. So linear regression, it's all about finding that straight line, right? The one that best fits the data, kind of like if you were drawing a trend line on a graph. And it's often used to predict things like, house prices based on their size, or maybe a student's exam score based on how much they studied.
Oh, okay. So if we like plotted those data points on a chart, right? Linear regression would be that line that comes closest to connecting all the dots.
Exactly. And if you need to predict a category instead of a continuous value, like will this customer click on this ad or not, that's what the logistic regression comes in. It's kind of the go-to for those yes or no prediction scenarios.
Gotcha. And we already talked about SVMs and their like knack for finding those optimal dividing lines, and k-means clustering, which always reminds me of like when I was a kid sorting my like massive Lego collection by color. It's amazing how this algorithm does something similar but with, complex data.
Yeah, it's a great example of how machine learning borrows a little inspiration from the world around us for sure.
Oh, yeah.
Now, what's fascinating is k-nearest neighbors, or KNN. It can actually be used for both classification and regression tasks.
Oh, really? So depending on what we're trying to predict, KNN can either like categorize data or estimate a continuous value?
Absolutely, yep. It all comes down to how you define nearest.
Mm-hmm.
Essentially, KNN looks at the k data points closest to the one we're trying to, classify or predict.
Mm-hmm.
And it uses either the majority vote or the average value to those neighbors to make its prediction.
So like if we were trying to predict whether someone will like a certain movie, KNN might look at the preferences of their closest friends, like their nearest neighbors in taste, and then make a recommendation based on that. But how do we know how many neighbors to actually consider? Like, is there an ideal K value?
That's the million-dollar question. Choosing that right k value is crucial, and it often involves some experimentation. You want to find that sweet spot, because a smaller k might make the model a little too sensitive to noise in the data, while a larger k could oversimplify things. And then you might miss some of those subtle patterns. It's all about finding the right balance for that specific data set and problem you're working with.
Sounds like there's a bit of art and science to it. Now, we talked about how decision trees are like flowcharts for predictions, but you also mentioned something called random forest, which, I don't know, that sounds a lot more, I don't know, intense.
Think of it this way. If one decision tree is good, multiple decision trees working together are even better. That's the essence of random forest. It combines multiple decision trees to try to improve accuracy and prevent overfitting.
Overfitting. Is that like when you study only one chapter of a textbook for a test, and then you totally bomb it because you didn't get the bigger picture?
That's a great analogy. Yeah, overfitting is when a model gets a little too fixated on that training data, so it doesn't generalize well to new, unseen examples. Random forest helps kind of mitigate this. It combines the predictions of multiple trees, each trained on a slightly different subset of the data. It's like getting a second, third, and fourth opinion from a team of experts.
Strength in numbers. So with random forest, we're essentially taking like a democratic approach to decision-making and machine learning.
Precisely. Now, another powerful ensemble method is gradient boosting, and that's where we combine multiple models. This technique builds models sequentially, with each model learning from the mistakes of its predecessors. Imagine a team of detectives working together to solve a case, each one building on the clues uncovered by the others.
So each model is like refining the investigation, getting closer and closer to the truth.
Exactly. And some popular gradient boosting algorithms are XGBoost and LightGBM, known for their speed and performance. They're often the secret weapon of choice in a lot of machine learning competitions. because of their ability to achieve that high accuracy.
From the sounds of it, ensemble methods like random forest and gradient boosting are like the heavy hitters of the machine learning world. But what about naive Bayes? That one's always seemed a bit, I don't know, mysterious, even though we touched on it a bit earlier.
Don't let the name fool you.
Yeah.
Naive Bayes is a really powerful algorithm, especially when you're dealing with text data. It's based on Bayes' theorem, which is all about calculating probabilities and kind of updating our beliefs as we get new evidence.
Okay, so like if I'm trying to predict whether an email is spam or not, naive Bayes would look at the words in the email and then calculate the probability of those words appearing in, spam messages versus legitimate ones, and then make a judgment call based on those probabilities.
You got it. It's like a detective analyzing, handwriting or linguistic patterns,
Right.
trying to determine the likelihood of a suspect's guilt or innocence. And because naive Bayes is relatively simple to implement, and it's computationally efficient, it's often a go-to for tasks like spam filtering, sentiment analysis, even things like medical diagnosis.
It's amazing how these algorithms can be applied in so many different fields. Now, speaking of applications, I noticed that your resources also include a section on time series forecasting. What exactly does that entail?
So time series forecasting is all about predicting future values based on past patterns in data. And this data is collected over time. Think stock prices, weather patterns, website traffic, basically any data point that fluctuates over a certain period of time.
Okay, so if I'm trying to predict, say, how many visitors my website will get next week, I'd need an algorithm that's specifically designed to handle that kind of, like, time-dependent data.
Precisely. ARAMA models are actually a really popular choice for time series forecasting. ARAMA stands for Autoregressive Integrated Moving Average. Bit of a mouthful, I know.
Huh.
But essentially, these models take into account the past values of a time series to try to predict those future values, like saying, based on how this stock has performed in the past month, here's where we expect it to go next week.
It's like having a crystal ball. But instead of magic, it's powered by data and algorithms.
Okay, we've covered a lot of ground here, different types of machine learning, a whole bunch of algorithms. But before we move on, how do we know if these models are actually any good? How do we measure their success?
That's where metrics and evaluation techniques really come into play. It's not enough to just build a model, right? We need to be able to assess how well it's performing its intended task. And just like we use different tools to measure distance, weight, or temperature, we have different metrics for evaluating machine learning models. It all depends on the type of problem we're tackling.
Okay, so if I'm trying to predict a continuous value like the price of a house, I'd use a different metric than if I was trying to classify data, like identifying those spam emails.
Exactly. So for regression tasks, where we're trying to predict a number, we often use metrics like mean squared error, or R squared. Mean squared error gives us an idea of how far off our predictions are from the actual values, on average. So a lower mean squared error would mean our model is making more accurate predictions.
Exactly. And then R squared tells us how well our model captures the variability in the data. So a higher R squared value indicates a better fit, meaning our model is explaining more of the patterns in the data. But when it comes to classification tasks, we often turn to metrics like accuracy, precision, and recall.
It's like having all those different ways to grade a test, right? Like multiple choice, true or false, essay questions. They all give you different insights into like a student's understanding of the material. So how do these classification metrics actually work?
So accuracy is probably the most intuitive. It just tells us the percentage of correct predictions our model is making. But accuracy alone doesn't always tell the whole story, especially if we have imbalanced data sets, where one class might be much more common than another. That's where precision and recall come in handy.
So it's like accuracy gives us like that overall picture, while precision and recall are zooming in on the specifics of like how well our model is identifying each class. It's like the difference between like judging a chef based on their whole menu versus how well they actually make like your absolute favorite dish.
Exactly. So precision tells us how many of the positive predictions our model made were actually correct. It's all about minimizing those false alarms.
Gotcha, gotcha. So if our spam filter is like flagging tons of emails as spam, but then a lot of them are actually legitimate messages, that would be a precision problem.
Precisely. High precision means we're catching the right things. We're not just casting like a wide net and hoping to the best. Recall, on the other hand, that's all about making sure we're not missing any of those important cases.
Okay, so if our spam filter is letting a lot of actual spam slip through the cracks, that's a recall issue, even if its overall accuracy seems high.
You got it. High recall means we're minimizing those false negatives, making sure nothing important slips past our radar. Ideally, we want a model with both high precision and high recall. We want that spam filter that accurately flags spam messages, but it leaves all of our important emails untouched.
Sounds like a delicate balancing act. Now, we've talked about evaluating a model's performance, but you mentioned something earlier about cross-validation. It's like giving our models a practice run before, like the big game, right?
That's a great way to put it. Yeah, cross-validation helps us assess how well our model is going to perform in the real world, on data that it's never seen before.
So instead of just testing our model on the same data we used to train it, we're giving it like a more challenging exam just to make sure it can really generalize what it's learned.
Exactly. One common technique is it's called K-fold cross-validation. So imagine dividing your data into K equal folds, kind of like slices of a pie. We train the model on K1 folds and then test it on that remaining fold. We repeat this process, each time holding out a different fold for testing. And in the end, we just average those results.
So it's like giving our model like multiple practice tests, right? Each
Uh,
one covering different aspects of the material. That way we know it's prepared for the real deal.
Precisely. It's definitely a much more robust way to evaluate our model's performance and ensure that it's not just memorizing the training data, but that it's truly understanding those underlying patterns.
This deep dive has been absolutely incredible. We've explored the fundamental types of machine learning. We peeked inside the toolbox of essential algorithms, and we even learned how to evaluate their performance. I feel like we just completed like a crash course in all things machine learning.
It has been quite a journey for sure, and really, it's just the beginning. The world of machine learning is constantly evolving, with new algorithms and techniques emerging all the time. What we've covered today is really just a glimpse, just a small glimpse into this fascinating field.
It's truly mind-blowing to think about all the possibilities, honestly, from like revolutionizing healthcare to transforming the way we interact with technology. I mean, machine learning is already making its mark on the world.
Absolutely. And as you continue exploring this field, remember, there's always something new to learn. So
Yeah.
dive into the areas that spark your curiosity, whether that's natural language processing, computer vision, robotics, anything. Anything that captures your imagination, really. There's a whole universe of machine learning out there just waiting to be explored.
So to our listeners, as we wrap up this deep dive, we'll leave you with this. What new algorithms or applications are you most excited to discover? What problems are you eager to solve? Using, the power of machine learning, the journey is yours to embark on.